Okay, thanks everyone. So I have a habit of changing the titles of my talk, and this time I'm going to keep the title the same but change the presenter. So as you may notice, I am not Kelsey Ortiz, so she unfortunately couldn't be here today, so you are stuck with me or my best implementation or representation of her. Okay, so the SEAQUE project, Space Entanglement Annealing Quantum Experiment, that is a project that started a couple years ago. Is led by us at University of Illinois, along with a colleague of mine in the aerospace department, and funded and coordinated by JPL NASA with important contributions from Thomas Yanavine's group at University of Waterloo and Alex Ling's group at Singapore and the company ADVR. So the goal, there are sort of two-ish main goals of SEAQUE. So one of them is trying to create an entanglement source in space using a new sort of technology that has not yet been flown yet with a waveguide source and an integrated optics source. And also along the lines doing a new sort of tomography of that using a single liquid crystal, and I'll talk about that in a minute. So that's sort of like the main first thrust. And then the second thrust is dealing with the fact that detectors in space get damaged by radiation, and that is going to be a limiting characteristic of all future space platforms, I guess. And so we want to try and understand that, and in particular see if we can prevent that using laser annealing on the detectors. Okay, so this is an exploded view of what the SEAQUE source looks like. So we have this entanglement. Let's see, is this more? Great. So we have a diode laser, just a simple 405 nanometer CW diode laser that pumps the entanglement source that's creating pairs of photons at 810 nanometers. There's a magical beam splitter that is going to be the key of producing the actual quantum state, and I'll come back to that in a second. And then we have entangled photons being transmitted and reflected, and we want to analyze. We want to do a polarization analysis of those. Typically, you would do that using a couple wave plates and some polarizing beam splitters, but we actually do that with a liquid crystal instead. And I'll talk more about that in a second. And then finally, we have the possibility of shining in a bright laser onto the detectors to do this annealing. Okay, so I'll talk just a little bit more about each of these. So this is a comparison of the other sources. As far as I know, the only other entanglement sources that have been flown in space so far. So at the top, we have the MISHIS experiment from China, which is a Sagnac source, Sagnac interferometer source, and then the source from Alex Ling's group, the SPOOKY satellite from Singapore, which is a beam displacer-based source. And you can see that in both of these cases, we're using bulk optics. In fact, the MISHIS experiment, because it's an interferometer, actually needed to be aligned, tweaked up after it was launched, which is not ideal, I guess I would say. And so this is a picture of our source. It's a waveguide source from ADVR, basically the size of a stick of gum. And we send into it, as I mentioned, 405 nanometer photons, and then they occasionally split into two daughter photons at 810 nanometers. And one of those is horizontally polarized, one of those is vertical. Now, you may notice that that is not an entangled state. So, and in fact, when the photons come out, because there's birefringence in the waveguide, one of them, the vertical polarized photon, comes out before the horizontal one. So we can send those photons through a polarization-maintaining fiber such that the horizontally polarized light goes a little faster than the vertically polarized light. And if you cut the length of that exactly right, then you can have those two wave packets align perfectly at the end of that fiber. And then after that, we launch into free space, and we go off of a beam splitter. We do a little bit of a trick where we rotate into the diagonal basis instead. So we rotate the photons by 45 degrees. You don't necessarily need to do that. It's kind of for technical reasons for us. But in any event, if we imagine that we have these one diagonal, one anti-diagonal photon on a beam splitter, they each act independently of the beam splitter. So they can each be transmitted or reflected. If both of them are transmitted, we don't want that. Throw that away. If both of them are reflected, we don't want that. Throw that away either. But half the time, one is transmitted and one is reflected. And to the extent that you, okay, so then we would have this state that's shown here, this diagonal right here. And to the extent that the two photons are indistinguishable from each other, which means they have to have exactly the same color and arrive at exactly the same time, you can then rewrite this in any basis, but in particular in the horizontal vertical basis, we get this state HH minus VV. Okay, so it's a post-selected entanglement source, but it's a relatively easy one. Okay, in terms of characterizing that, normally, as I mentioned, with quantum state tomography, one would typically use, for example, a couple wave plates to do this. And it turns out no one wants to have a rotating optic in space. The engineers are really opposed to that, so they prefer using things like liquid crystals. Typically for tomography, we want to measure, for example, if you know this, like in the horizontal, vertical, diagonal, anti-diagonal, and left circular, so these mutually unbiased bases. But it turns out you can pick a different triad if you can use, say, a liquid crystal at this magical angle of 27.35. When you change the voltage on the liquid crystal, you sweep out this circle, and the other blue dots here are shown make a perfect triad with that horizontal. And so you can do a full quantum state tomography with that. There are some issues that liquid crystals are not as nice to use as you might like with wave plates, and if someone wants to ask me later about that, happy to talk about that. Okay, let's talk a little bit about the detectors. So it's been demonstrated in numerous experiments that if you put avalanche photodiodes up in space, they will get radiation damage that will lead to an increase in dark counts of something like 100,000 counts per second over the course of the year. Now, in some eventual application where maybe you're only getting 50 entangled photons per second from some ground source to your satellite, 100,000 noise counts is not a good thing. Obviously, it'll prevent you from doing anything. So it's also known that you can cure this damage if you can heat the detectors. So if you put them in an oven at 200 C for about an hour, so the damage will go down. People don't really want to have big ovens and heating things for a long time in space. The thermal management is a problem. So it turns out the other thing you can do is called optical annealing or laser annealing, where we shine, say, a 1-watt laser onto the detector only for about a minute, and it has the same impact of suppressing the dark counts. That one has to be careful. So if you shine a 5-watt laser onto the detector, you will set the dark counts absolutely to 0. You will also set the efficiency permanently to 0 because you basically burn out the detector. Okay, so the goal of SEAQUE in this case is to use this periodic detector annealing because we want to see if we can extend the mission lifetime over longer times and basically see in a real-time situation where you're accruing damage, you're fixing it, you're accruing damage, you're fixing it. Do you come back to the same baseline? Are there some unannealable dark counts? We just don't know, so that'll be interesting to find out. Okay, so we've more or less packaged up this whole system. It's a pretty kind of a small box. With the laser and the source are sitting under this platform. They go through some fiber optic cables to our free space optics and then loop back around to the detectors underneath here. So we've done full system testing, we've done vibration testing, and yay, the thing survived. That's by no means an easy thing because you have to couple into single mode fibers and have the whole thing shaking. You know, most of us wouldn't want that in our laboratories. And show that we can still get a Bell violation, before and after. Actually even got a little bit better afterward because the thing was originally quite cold and then it heated up over the course of the vibration. And when you change the temperature, you cause the wavelengths of the two photons to shift and they come more into resonance, which is why our results got a little bit better over time. So this is due to be launched into space. It's being packaged up by Aegis Aerospace, and it will then be mounted on the outside of the ISS as part of the Materials International Space Station experiment, the MISSI experiment, and we expect then to get daily downlinks of data. And then at the very end, they tell us that they will be able to return it to us, which will be great because then we can do a complete analysis and look at radiation damage on the crystals and such. So just what's coming up for us in the rather short amount of time. There are a couple hardware issues that we're still trying to diagnose with this, with great help from our friends from ADVR. And we had to replace one of our liquid crystals, so we're in the process of doing that. And then we are supposed to deliver this to Aegis on May 1st, and it should be launched in September. And then hopefully it will be in the air for about a year. Okay, so I will do my best to answer questions. But a friendly person, if you want the real answers, you could also reach out to Kelsey Ortiz. I'm happy to answer anything I can.
Question.